Today, we're going to explore the hidden world that's right under our feet and just behind our walls. I'm talking about drainage system engineering. And you'll see it's really a mix of hard science and some pretty clever design, all working towards one simple goal, making water go exactly where we want it to.
I mean, really think about it for a second. You got hundreds of floors, thousands of sinks and toilets. All of that wastewater has to go somewhere, and it does it silently and efficiently. So how on earth is that possible without a huge, complicated mess of pumps running 24/7? Well, the answer is surprisingly elegant.
You know what it is? It all comes down to gravity. A gravity-fed drainage system is just a beautiful lesson in physics. It's a whole network of pipes, where every single one is angled just so to let nature do all the work. Now, this isn't guesswork, not at all. It's a science that's governed by really strict rules, like the Saudi Building Code, or SBC, and the International Plumbing Code, the IPC. Think of those as the official playbooks for plumbing.
So, how does an engineer actually sit down and design one of these systems? What are the tools and the rules of the road they use to turn a drawing into a perfectly working drainage network? Let's open up the design kit and take a look. Okay, so here we go. These are the 5 core steps for any pro drainage design. First, you've got to pick your pipe material. We're talking uPVC, cast iron, that sort of thing. Second, you figure out the total wastewater load using something called drainage fixture units, or DFUs. Third, you apply the right slopes to your pipes so gravity can do its thing. Fourth, you got to put in cleanouts for maintenance down the road. And last, but definitely not least, you install a vent stack so the whole system can breathe. We're going to break down every single one of these. All right, let's get into the real nitty-gritty, the core logic. We're going to see how those steps translate into actual, precise calculations. This is where the real engineering happens. And it's all about a set of fundamental rules that make sure everything flows just right. So the whole system, the whole design, is built around this one key idea: the drainage fixture unit, or DFU. The easiest way to think about it is like traffic points. You know, a small sink might be 1 point, but a big toilet, that could be several points. You just add up all the points, and that tells you exactly how much traffic your pipe network has to be able to handle.
Now check this out, because this is where it gets really interesting. This cable shows a super important relationship. A smaller, 50mm pipe needs a steeper 2% slope to keep things moving. But as the pipe gets bigger, say 100mm, it can get that same flow with a much gentler 1% slope. It's a total balancing act between the pipe size and gravity. And you might think, oh, a 1 or 2% slope, who cares? Trust me, over a long run of pipe, that tiny difference is everything. It's the difference between a free-flowing system and a constant headache of blockages and expensive repairs.
So here it is, the main takeaway. This is the golden rule of drainage design, period. The more DFU traffic points you're dealing with, the bigger your pipe has to be. It's that simple, and it's absolutely non-negotiable if you want to prevent backups and make sure the system can handle whatever you throw at it. Okay, so we've got the rules for the individual pipes down, but how do all these pieces actually come together to form one complete, living, breathing system that works in perfect harmony? Let's find out. Think of this as the master checklist for putting it all together. First, you calculate your total DFUs. You got to know the load. Then, you size your pipes and set your slopes based on that load. Next, you have to strategically place cleanouts for future access. And this is a big one. You install the vent stack to balance the pressure. And of course, every single one of these steps has to be in full compliance with the official code. And that brings us to the unsung hero of the entire drainage network, the vent stack. You can honestly think of it as the system's lung. It's what equalizes the pressure inside the pipes. This stops water from being siphoned out of your P-traps, and, this is really important, it safely vents nasty sewer gases out of the building. Without it, the whole system just doesn't work. Okay, enough theory. Let's see how all these ideas and rules come together in a super common, real-world scenario. Let's design the drainage for a standard bathroom. Right, first things first, we start with the fixture that has the biggest load. That's the toilet. According to the code, a standard toilet gets a value of 3 drainage fixture units. Next up, we've got the wash basin. You know, the sink. It's a much lighter load on the system, so it's only assigned a value of 1 DFU. And finally, we have the floor drain, super important for cleaning and preventing overflows. This one gets a value of 2 DFUs. So, let's do the math. We've got 3 plus 1 plus 2,
And that gives us a total design load for this whole bathroom branch of 6 DFUs. Simple as that.
So what do we do with that number? We take that 6 DFU value right back to our codebook, and it tells us that a load of 6 DFUs needs a branch line pipe that's 75 millimeters in diameter, and it has to be installed at a 1.5% slope. This branch then connects into a bigger 100 millimeter main line, which, you might remember, only needs that 1% slope. See? It all just fits together perfectly. So there you have it. That's the logic behind a professional drainage design. Every single pipe, every slope, every connection, it's all precisely calculated. But you know, the design is really just the beginning. The real challenge is making sure this system works flawlessly for the entire life of the building. And that, well, that's a story for another time.